All right, so welcome to the last ENGR 315-A that you will have. I know you have all your microphones muted, so I can't hear you crying. It's fine. Just hold yourself off to get together. We'll get through this. It'll work. Okay, so as said, today is review day. Any questions that you would like to have answered prior to the final, I'll be happy to work through all that kind of good stuff. Like I was just saying to Danilo, the final itself has 3 questions nominally on it. One of them's a thin wall pressure vessel problem, so that should take you all of like a minute and a half. Should be straightforward. It should be a 2-hour test, and you have a 3-hour block to do it in. We'll do it in the same format as that we did the last test. So come online around 8 a.m. on Saturday morning. I'll be here. I'll send you the test in a PDF file shortly prior to that. You just have to do it out, and then scan it to a PDF and submit it back to me on Canvas. So that's the deal. It's open book, open note. Please not open internet because that doesn't sound right. Just use your books and your notes, and we will run with that. So, are there any questions that you'd like to see answered?
I don't know if you just went over this, Brother Morris, but it's going to be like similar to the last exam
in terms of
like setup?
Like in terms of like I send you a PDF file, you'd work on your paper and send a PDF back to me? Is that what you're asking?
Yeah, that, but like, is it going to be like one question, multiple parts, or multiple questions, or?
Okay. Yeah. So there are nominally 3 questions on it. One has a few different parts, and one of them should take you like a minute and a half.
Oh, okay.
I might be exaggerating on the minute and a half by a little bit, but not by much.
So there's like 3 questions though?
Nominally, yes.
What do you mean?
One because one is more than one parts.
Oh, okay. So there's like okay.
Yeah.
Okay. So let me think. It's gonna be on I'm having a brain fart. Why can't I think of this? Pressure vessels, right?
Say again?
It's going to be with pressure vessels, like pressure vessels going to be on there?
Yeah, so that really short question's the pressure vessel thing. It's going to it'll touch on just about everything that we've touched on this entire semester.
Okay, well, I'm going to write down. So, pressure vessel. Then how else could we like prepare and like study and everything like that, basically? Because what's a good way would you say?
You can read back through your notes. You can look over all the homeworks that you've done. You can look in the book, look at example problems from the different chapters that we've done. You can do. There are problems in the book that you can do. So you can do those. I call even if you don't have the answer guide, which I assume that someone does because someone always has the answer guide. That you can do those problems and you and I can go over them. I'm happy to facilitate that. So those are all good ways to study for it.
So like what chapters then would be a good like? Is there like chapters I can?
Let's see. Let me look at what's here. So let's see. Stress and strain is chapter 2. We usually didn't do if you have the book. I think a lot of the sections have asterisks on them. We didn't do those. If it's not in your notes, we didn't do it. Let's see. We did chapter 2, 3, 4. Let's see, 7, 8, 9. Yeah, we did all those. Yeah. And yeah, we didn't do anything with a asterisk on it. If you have asterisks on your section numbers, the way that I do. Anything from there is fair game.
So wait, you said what's the chapter it starts with? I don't know if you, what was it like?
1, 2, 3. Hang on, let me flip back to it now. 1, 2, 3, 4, 6, 7, 9. Essentially, you can look in your book and the chapters that sound like we did do them, we did them. Like when it says bending or stress and strain axial loading or torsion or transformations of stress, deflections of beams. We did those things.
Okay.
Sorry, we did not. Sorry, we did not do 6. We did not do shear stresses and thin wall things.
Okay.
Yeah.
So I guess I mean just review your notes. I mean, I'm just trying to like.
Yes. Yeah. So everything I just said is a good way to study. Reviewing your notes is good because it lets you know what all we did, what all whole topics we covered. Doing problems from the book can be useful because it means that you try new and different problems. Looking back over your homework is good because you have the answers to that directly as well as feedback on it. If you don't have the answer key to the book, you can go through the book and check on things because it's hearing the material from different sources. These are all good ways to study. No one way is necessarily the best. It depends on how you learn best. So those are all good ways to. Those are all good ways to do it. Feel free to use any of them that make sense to you. I honestly don't know what the best way for you to study is, but those are all different resources that you can use. Maybe it'd be best to start with your notes and your homework and see if you have questions, and then you can go to the book for more. I don't know, but that'd be my take on it.
All right. Well, I mean, I guess that's all the questions I have. I don't know if anyone else has questions, but
can we go over how torque and strain are related?
How torque and strain are related? Yeah.
Like where is it?
Is that going to be on the exam? I don't even know. I don't even remember about torque and strain. Like I know torque and strain, but I didn't think together.
It's called yeah, it's it's called we talked about it back before spring break. Called strain. How do we say this? We derived torsional stress from the amount of from the strain that it produced. But which call but we can have a look at that again. Let me just pull that up. Sorry. So Nick, if you are thinking like where you can find it, go back to like notes from like week 4 or 5 of class. We talked about torsion, and there'd be stuff about strain and shear. It's called shear stress and torque and stuff like that. Let me just find my thing again. Okay. Okay, so Annabelle, what about it do you want to go over? Do you want to see like a problem with it? Do you want to like go through the derivation again? What are you looking for?
Can we just do a problem with it? And like,
Okay.
Is there a chance that something would have a torque, and then we would have to like analyze the shear and bending moment diagram?
Gotcha. I'm going to try not to be that complex on the exam, but
Okay.
we can certainly talk about what that might look like. We'll start from something a lot simpler though.
Okay.
Cool. So let's run over to the camera of documents. Okay. All right. So, say I have a shaft. One hidden line there. Cool. Has some OD 0.25 inches. Has some ID. .5 inches. All right. And because I have a cylinder here, let's give it a length. All right. So we have some hollow shaft. It has an inner diameter that we know, an outer diameter that we know, and a length that we know. Let's assume that it's fixed at this end. Yeah. And we're going to start cranking on it. So there's some torque. Well, 37.7 kip inches. Another way of saying this, if it makes it a little bit more familiar, be like 3,770 pound inches or inch pounds. Oh, sorry, there should be another zero there. Okay, so we got this. The question that we want to answer is what the which call what is the which call what stress is being caused by that torque that we've applied. Okay. Is everyone on board with that?
Yeah.
Okay. So let's play. So let's play the game. So
Wait,
in order
can
to
you
find,
that, Brother Marius? I wasn't
Sorry.
sorry about that.
sorry.
No, you're good.
Brother Marius.
Yeah. What's up, Cade?
Brother Marius. While Nick copies this down, I have an unrelated question.
Okay.
When I come back to fly, will I get credited for this semester? When I finish? I should, right?
So like when you finish your instrument rating, will you get a grade for your instrument lab?
Yes.
Is that what you're asking? Yeah.
Because I took it this semester.
Yeah. It's called it does remind me we do need to fill out a incomplete form for that, so that, or it's called, is either an incomplete form now or a change of grade form later, because grades are due by the end of like next week or whatever. But yeah, it'll come back to credit you for this semester in terms of grades. Yeah.
Perfect. Thank you.
Yep.
I'm good, Brother Marius. Thank you.
Sweet.
Sorry about that.
No, I should have asked.
No, you're
All
good.
right. So, if we want to find stress, the first thing that we want to do is, well, I mean, what's the first thing that we've always done, right? In terms of like our beam analysis and such, what have we been doing in order to find our internal loads?
Find stress.
Okay, and how do we find stresses?
Well, normal stress is force over area.
Yeah, but that's not the question I want to ask. So, yeah, Annabelle?
Cut a section.
Yep, cut a section, because we can't know anything about the inside if we don't cut a section. So there are only two loads here. It's fixed on this end, and you have a torque on this end. There are no forces acting on this, just this torque at the end. So that means that just kind of looking at it, we know that there are no external forces because we didn't apply any. So even though this end is fixed, probably not going to be any forces because there aren't any other forces. However, it's fixed and there's a torque here, so we know that there's probably going to be a reaction torque there. So let's call that RT. And if I did a sum of the torques here, be like what? T plus RT equals 0. So we can tell that these two are going to be equal and opposite. Okay. So we know all of our external stuff. Let's dig into the internals. So to do that, I'm going to cut ourselves a section. See if we can cut one right around here. It's hard to draw on a curved thing, so this is my section line. I'm going to cut a section there, right in the just in some arbitrary location. Doesn't matter because there's only a torque on each end. There's nothing else in the center, so it doesn't matter where I cut my section. It'll still look the same. So there's my section. There's my torque that I've applied. There has to be some reaction torque. Can't draw with a darn when it's in 3D. When it's in 3D. I'll call it torque internal. Okay. And what the heck? There's a coordinate x. So if I do my summation of torques, I'm going to find again that T internal is equal and opposite to my applied load. Does that make sense?
Yeah.
Because if so, I'm not going to bother. Great. Okay. So that means that this guy, this is an internal load, and this is what actually causes stress, right? Like that's why I've been playing this game all semester where we cut sections, because it's these internal loads that cause stress. The stress is a transmission of a force or a torque through a material. That's how it gets how it gets transmitted. So so we know that this internal torque is what's causing our stress. Back when we talked about torsion and torsional stress, we figured out that torques cause a shear stress, and it looks something like that. We have that expression for it, where this is our internal torque. This is the radial location that we want to find stress at. Sorry, radial. And what was J again?
Wasn't that like a constant we found in the book or something like that?
It is something that we found in the book. Yeah. Sorry, a lot of people were talking. What's up?
I don't have anything.
The polar moment of inertia.
Yes. So J's polar moment of inertia. We found it it's the back cover of the book. Inside the back cover, you'll see a bunch of J's listed. It's either on the origin, JO, or the centroid, JC. So you just have to pick the one that fits for whatever problem that you're looking at in terms of what shape and where it's rotating around. Shapes always rotate around the centroids, so JC is usually what you want. So like for a circle, the polar moment of inertia that we'd use would be half pi r to the fourth, for example. So thing is, what I have here isn't one circle, it's a hollow tube, right? So if I look at my cross section, looks like that, right? So how do I find the polar moment of inertia for this section when this is my solid material, this hole here, it's a hole, so it obviously doesn't contribute to the polar moment of inertia.
We subtract the radius or the diameters or the radius, if you want to say, the two diameters from each other.
Not quite. The trick is that moments of inertia can be added when they're around the same axis, right? Or subtracted. So we're not going to subtract the radii. We're going to subtract the polar moments of inertia. So here's my OD. Here's my ID. I know that polar moment of inertia for a circle is 1/2 pi r to the 4th. So the J for my section, will be the polar moment of inertia of the big circle. So 1/2 pi OD over 2 to the 4th minus the polar moment of inertia for the small circle, so that I'm left with just the stuff that's actually material and not the whole. Okay, so this does end up looking something kind of like what you were saying, Nick. End up with if you simplify it, you get something that looks like that. So you kind of are subtracting radii, but it's radii to the 4th, or in this case, diameter to the 4th, because it's a subtraction of polar moments of inertia. All right. So that gives us our J. Looking back at this, we got J. We know what our torque is. All that's left is we have to figure out what radius we want to find the stress at. Let's wait for you guys to finish. All right. So now that we have those guys, the question is, where do you want to find stress? Because if the shear stress varies with radius, then I have some stress distribution, right? So if I draw as like heights, be like something like that. I have some increasing amount of stress depending on where I am along the radius. So if I want the maximum amount of, so if I want to find shear stress on the surface, say, what would I put in for R?
.25 divided by 2.
Yeah, I put in the outer radius of the circle, right? So if I wanted to find stress at that point there, that guy, it'd just be the OD divided by 2. It'd be the outer radius. If I wanted to find stress at this point here, be the inner radius. Pick a point in the center, just be whatever that radius is. The distance from the center to whatever point I wanted to find stress at. as a child. Just plug that in. I just find that and plug it in for R. So I can do that. I get an expression for the shear stress caused by torque at that point. Bam, done. It was called Annabelle. You had asked about shear strain originally, I think. If I wanted to find the strain at that point, well, I know from Hooke's law. So we had Hooke's law for normal stress, right? Now is that you have a normal stress causes a normal strain. And they're related by Young's modulus. You also had one for shear stress, where a shear stress causes a shear strain. And they're related by the modulus of rigidity. So if I have my shear stress, I can just divide by modulus of I can just divide this by modulus of by my modulus of rigidity if I know it. It's just because it's just a material property that I can look up and or whatever. If I divide my shear stress by my modulus of rigidity, by definition, I get the shear strain at whatever the radial location that I'm looking at.
Wait, so Brother Marius, we're solving for the tau xy in that equation, or that problem, right?
Yeah, tau xy is your shear stress, which we go back to our original thing. That was the question that we were asking. How much stress is caused by the torque? So the torque causes a shear stress, so we can solve for shear stress directly based on that torque.
What I was gonna say is like the torque is okay, so it's still the same at the R, like because you said the T internal, like that, it's still the same as the normal torque, the T, right? Label.
Yeah. So if I cut a section here,
Yeah.
I get this free body diagram.
Yeah.
So I have some reaction torque, and the only other thing in my free body diagram is the applied torque. So if I did a summation of torques, they'd be the only two things in it. Therefore, same as here, when I looked at the reaction torque on the wall, it was equal and opposite. These two will have to be equal and opposite. So I know that my internal torque has the same magnitude as my applied torque.
Okay. Because I have the sum of the torques there. Like I'm just saying, but like, no, I guess yeah, it would be equal. And now that's why, because you just plug it in. Okay. Never mind. Okay. Sounds good then, because you were okay. That makes sense then. Okay.
Cool.
I forgot about some of the torques there. That's why I was like, wait.
Cool. All right. So Annabelle, does that get to where you wanted to go?
Yeah, that's good.
Okay. Anything else that you wanted to go with that?
I guess if there was a force pulling along the axis too, we could just do more circle by adding the normal stress that creates to the shear that we just calculated, right? Okay. Then
Yep.
Yeah, good.
So if I started pulling on this with some force P, say. It's the only force here, so equal and opposite reaction there at the wall, right? At the fixed boundary. So once I find my shear stress, if I look at my cross section again, you can do a side view. So I have torque, some force. You know that everything's equal and opposite. So you can draw the internal side of my free body diagram kind of flippantly in a sense, because I only have one force in this whole thing and one torque in this whole thing. So I know that everything's equal and opposite here. So I know that normal stress is just force over area, so like P internal divided by what? There's area. And then I can combine those with more circles. Say that I wanted to find my maximum shear stress. Well, sure, we have this shear stress here, but because we have another stress acting at the same section, and this we assume is uniformly distributed over the section, that means that the actual maximum normal stress is going to be higher. And we can kind of figure that out through Moore's circle, particularly through the radius of Moore's circle. So that'd be like radius equals sigma x minus sigma y over 2 squared tau xy squared. And we call this my x direction. That's a sigma x. There weren't any other forces, so sigma y is 0. I can just plug into this guy and get my max shear stress.
And then if there was a force that was like pulling down on it,
Like
would you that?
that?
Yeah.
Cool. Yeah, so now it's bending, right?
Yeah.
So now I need to figure out what the bending moment is at whatever your section is, as well as your shear stress caused by that bending, and add everything together. Again, through kind of the same idea as this, except going back to, oh gosh, what homework was it? It was one of the bending homeworks. We also did an example in class with the kind of, it was a thing that looked like that, pulled on each end, and because there's some distance between this bowed up section and the line where the forces are applied, there's some bending moment as well as a normal force in that section. So we had to add those two stresses together. That's kind of the idea that you'd be going at this problem with when you add this downward force here. I'm going to try to be not that tricky on the test, but it's a good but it'd be a good thing to know how to do.
Brother Morris, I don't know. I'm having a question. So we have our sigma x, okay, out there for the equation. But then is sigma y just 0 then, since it's not really moving in the y or
is there a force in the y on our free body diagram?
No.
Correct. If there's no force, is there stress?
Yeah, no. There's no stress. Okay.
Correct. So
I just wanted to make sure I was understanding that correctly.
Yep.
So then that's what you were saying, that to break back there with AB, that if it did go up or something, that is like a force in the y, so there adds more to it.
This is a force in the y, but am I trying to like compress this thing in the y or pull it apart in the y?
No.
So I still have no stress in the y direction. But what this is going to do, it'd be like if I had my rod here, I fixed this end, right? This end's not moving. That's kind of what I have here.
Mm-hmm.
And then I put a force going up or down, right? So
yeah.
it's bending in addition to twisting and being pulled. It's also bending.
Okay.
Well, if I did it with something that maybe was a little bit easier to see deformations on, instead of just being pulled and twisted, it's also bending.
Okay. All right. Okay. I just wanted to make sure I was understanding that, because I get what you're saying with the bending, yeah, but I just want to make sure the sigma xy stress. Okay.
Yeah. I'd be happy to run through an example for that and post it later. I just don't have. We only have like 6 more minutes of class, so I'd be happy to whip that together though.
Yeah, I mean, I think that'd be beneficial for the bending at least, like how that was. I mean, I think that'd be beneficial. So, unless did you say that's going to be on the exam, or is that not going to be on the exam?
I was saying him that might be too convoluted, but definitely you throw up an example about it. It'd be a good practice for combining stresses, because doing problems that are harder than what you actually have to do is good practice. Makes the stuff you actually have to do easy.
Mm-hmm. Okay. Yeah.
Any other questions?
I don't have any more questions, but
Is there any examples that people would like to see a worked version of?
So my question is kind of, how are we going to combine like everything into one problem?
That's why there are 3 problems.
Oh yeah, good point. Okay. But even so you said like there's like one problem with a couple parts and then another problem with, you said another problem is the pressure vessels. But I'm just trying to think. I mean, unless you have a beam that's twisting, bending, and like you just said, that's how I could think about it, maybe with point loads.
Well, that's why there are 3, and that's why there are 3 problems at least. 3, there'll be three problems. One will be a beam, one will be a pressure vessel. The third one might have a torque on it.
Okay.
Should we go over strain and like how it can change the length of a beam if it's under pressure like that, I guess.
Right. Yeah, I wouldn't do anything beyond what we did in class. So, yeah. So like, I probably won't ask you to find the strain of a beam in bending or something like that. You should be able to know. You should know how to do that, but I'm not. I'm not going to ask you to find it. It's a little too finicky,
Okay.
nitpicky. That's the right word. Just because it's not really something that we focused on. We mentioned it, but we didn't focus on it. You definitely should call it. It's something that you definitely should know how to do though.
I don't know. I mean, if I have any other questions, I guess I'll be in contact with you. But off the top of my head right now, I'm not really.
All right. Well, I'll work this out, and I'll put it up. I'll try to get that done today.
Okay. Thank you, Brother Morris. I appreciate it.
Yep. All right. I will see you on Saturday, 8 a.m. and at.
Yep. Sounds good.
All right,
Have a
thank
good
you.
one. Have a good one.
Y'all